Over the past year, I've been playing a lot more games than usual. Something about recent world events has made it my choice pastime. I even bought a new laptop, biting the bullet and making the switch from Mac to PC, so that I could join #PC Master Race and play games the way God intended. A lot of this gaming, I'm only slightly embarrassed to admit, has been Fortnite. Now, before you accuse me of either being 10 years old or having trash taste in games, let me tell you, only one of those things are true. And I just drank some of this the other day. So since I'm a newly converted PC player, I've been familiarizing myself with graphics cards and all the crazy settings that come with them. One of those settings I found to be particularly fascinating, and that's where the idea for this video was born. My idea for this channel is to upload edutainment style content, starting with computer science, and maybe adding more as I go, if anyone actually winds up watching these videos. Anyways, so the interesting feature I found was Nvidia DLSS. This is a setting available on RTX cards only that helps boost frame rates, and it's made my aim in Fortnite twice as good. When I looked into DLSS, I quickly learned that it had a particularly fascinating piece of machine learning at its core, and I thought I'd upload a video trying my hand explaining it, so here that goes. After recording the explanatory bits and then writing this intro, I realized the video was too long, so I've split it into two parts, so definitely go check out the second part after you're done with this one. I hope you enjoy, or at least learn something new. Alright, so before we talk about what DLSS is, we should probably define the acronym, what it stands for. So DLSS stands for Deep Learning, for the DL portion, and then SS stands for Super Sampling. And so these are actually two separate concepts, and we'll be covering them separately. So in the first video, I'll be talking about the deep learning portion, and sort of giving a high-level overview of what machine learning is and how we can leverage it. And in the second video, I'll discuss what super sampling is, and then we'll bring the two together to then dive into the finer points of DLSS and what it is and why it works. So let's say this part will be video 1, then over here we'll have video 2. Alright, so let's talk about that first part of DLSS, the deep learning bit. So deep learning is a subset of the broader machine learning field of computer science. Machine learning strives to get computers to be able to generate and infer solutions to problems and questions humans might have without the human programmer explicitly finding and engineering the solution himself or herself. If that sounded confusing or just like nonsense, give me 5 minutes to explain. So in traditional programming, the style is more imperative. There might be some question or problem that needs addressing, and a human programmer or a team of programmers gets together and they find the solution themselves. They find the answer or the steps that will generate an answer, and then they give a set of instructions to a computer to run. This is basically just the sequence of code that a programmer might write. With machine learning, though, we actually switch this up, and instead of telling the computer exactly what to do to solve the problem, we actually tell the computer, we give it a set of instructions on how to learn. We tell the computer how to infer patterns, and then we actually also give it a huge data set to learn from. And then the computer sort of just sifts through this data set and it starts to pick up on patterns. These patterns might not be things that humans even think about. So for example, in an image recognition problem, if we were trying to differentiate or get the computer to differentiate pictures of cats versus dogs, humans might have a set of criteria in mind. Let's say that maybe the shape of the snout or the eyes or the pattern on the fur might help us associate whether the picture is a cat or a dog, but computers will come up with crazy inferences on their own. And so we sort of just let the computer run wild and figure out its own representation that helps it learn what a cat and dog is. So at its core, actually, or at its simplest, I guess, machine learning can sort of be viewed as a line of best fit or a curve of best fit problem. You might recall that in algebra in middle or high school, you might have done problems like this. So let's say you have a graph with a bunch of points, so like a scatter plot. Let's say the points look something like this. Oops. I don't know why that happens sometimes. Here. So the points look something like this. The line of best fit here might look something like that. Or if we were looking at curves, we might see something like a data set that looks something like this. And the curve of best fit might be some sort of polynomial or exponential that looks like this. The reason this is a good approximation for ML is actually some of the simpler ML algorithms really are just linear and quadratic regressions. But the idea is that this is sort of a predictive model, sort of like a machine learning model. Let's say each of these data points is a picture of a cat or a dog. And then now when the machine learning algorithm or classifier, as they're called, is run amok, run loose on Facebook or something, when it sees a picture of a dog or a cat that it hasn't seen before, that would be a data point that doesn't exist here. So let's use a different color for that. That would be a data point, let's say over here, right? And so essentially, to predict the value of this, right, you might extend the curve up this way, and the point would be somewhere over here. So a little bit messy, but I hope you get the idea. This might not be best for a binary question like, is it a cat or a dog? But let's say we were predicting stock prices or something like that. It becomes a little bit more clear that a line of best fit is exactly what we're looking for. But the types of machine learning algorithms that are that you'll typically come across for, say, something like facial recognition on Facebook or natural language processing that allows Alexa or Google Home to recognize your voice, they're not as simple as linear regression, line of best fit, or quadratic regression, curve of best fit. These are way more complex models, but they still perform the same idea of fitting a model to a set of data points. The data points, though, are not necessarily on a plane or even in three-dimensional space. These are data points that could have arbitrary number of attributes. So you can think of it as n-dimensional data points. If that doesn't make sense, don't worry. That's just a bit of a implementation detail, I guess, of machine learning. So the specific model that we're going to be talking about today that Nvidia uses in DLSS is actually called a neural network. So again, in the last maybe 5 years, 5 years probably, machine learning has become a bit of a buzzword and has entered the common consciousness, I guess, in pop culture. So you may have heard of a neural net. So this idea, let's write it down over here, neural network. So I'll just abbreviate it as NN from now on because my handwriting is absolutely atrocious. So you may have heard that the neural network takes inspiration from human biology and in specific the brain, right? Hence neural network. It seeks to model problems as sets of intertwined and interconnected neurons, just like your brain does. And then similarly to how the saying in biology and neuroscience is like, I think it's neurons that fire together, wire together. Something very similar happens with machine learning. We essentially have these layers and layers of interconnected neurons. And then during the training process, when we train the computer, and that's essentially the learning phase, certain connections between certain neurons get strengthened and certain get de-strengthened or weakened, I guess. And this basically helps the computer make associations, and it allows the computer to classify a certain voice as mine versus my friend's, or a certain picture as a cat or a dog. So what does this look like? So there are plenty of videos online about neural networks, even on YouTube, that explain it much better than I could in this video about DLSS. But all neural nets look something like this. You have one layer of neurons. So these individual circles are neurons, and these are your inputs. So in this case, the neurons are actually just pixels for an image. So the image or the frame that we're looking at for DLSS, it gets decomposed. So if it's a grid of pixels, these pixels get mapped into individual neurons. And then you'll have successive layers of hidden neurons. And then these will be wired together like this, where each neuron gets wired to every other neuron in the next layer. So you can imagine that it's this very complex mess of wires. But what happens is when we train, we actually will strengthen certain connections and weaken other connections. So the connection between this guy and this guy might get strengthened, this guy and this guy might get strengthened, but maybe the connection between this guy and this neuron will get weakened. Let's just make it white to show a weaker one, I guess. So this is admittedly a bit of a mess. If I can find a better diagram, I might just put it up here briefly to show. But I hope that this sort of gives you the general overview. So the deep portion of deep learning actually just comes from the fact that these different layers we have, and it goes on for a while. Deep just means there are many layers. There are many of these hidden layers, they're called, if you're interested in looking up more. Hidden layers. That refers to all of these. And then after all of the hidden layers do their computation and subclassification, they will output, let's use green, I guess, maybe. They will output a set of final neurons, and these final neurons will actually encode the solution to whatever problem you were thinking of, whether that be classifying pictures of dogs and cats or classifying human voices.